Yes. Let us solve a problem on finding the collapse load in the case of a simply supported beam subjected to a concentrated load like this. So before analyzing the problem, so we should know what are the conditions to have the collapse mechanism in a steel structure. Suppose if R is the redundancy of a structure, then number of plastic hinges to be formed, to have collapse mechanism will be R plus 1. So this is general guideline. So here, in the case of a simply supported beam, suppose you take a simply supported beam, so the redundancy is 0 because simply supported beam is a statically determinate structure. So number of plastic hinges to be formed will be 1. So one hinge is enough to form collapse mechanism. If you take a fixed beam, in the case of a fixed beam, the redundancy is 2. Therefore, you require 2 plus 1, that is 3 hinges to be formed to have the collapse mechanism in the case of a fixed beam. In the case of a proper cantilever, you will be having the redundancy as 1. Proper cantilever beam, you have R is equal to 1. So therefore 1 plus 1, that is 2 hinges are required to form the collapse mechanism. So this is a fundamental thing you should remember. So depending on the type of the beam, you can fix the number of plastic hinges to be formed to have a beam mechanism. So that mechanism is called as beam mechanism. That means when the structure is loaded up to ultimate load, we can take the value. So when the collapse load occurs, or when the beam is subject to collapse load, then the mechanism will form. So mechanism means failure. So in case of a beam, we call the mechanism as beam mechanism. So in case of frames, you have sway mechanism also, you have joint mechanism, you have combined mechanism. There are 4 types of mechanisms. So in the case of beam, you have only beam mechanism. So the thing is, we should know one more thing, that where all the plastic hinges form. So formation of plastic hinges will be at critical points. Plastic hinges will be at critical points. So that point will act as a hinge which can have infinite rotation. So here one point is plastic hinge may form at the point of maximum bending. At maximum bending point it can form. At the point where concentrated load acts. So under concentrated load or point load, it can form. Then plastic hinge may form at the point where the cross section of the beam changes. Cross section of the beam changes means the value of moment of inertia changes. So sometimes what happens, you may have a beam something like this. You see, a portion of the beam is simply supported beam, but it has got 2i value from here to here and I value from here to here. In this case, you can expect a plastic hinge here, because this is section where the cross section area will change. Suppose if you have a concentrated load, there is a possibility of having plastic hinge here also. And at the supports, you don't have any plastic hinges here. because at the supports you have bending moment 0. In the case of a simply supported beam, at the supports you have bending moment 0, so therefore you don't have any plastic hinges at the supports. So these are some important points we should keep it in mind. Before analyzing the problem of finding the collapse load, we should locate the position or the point of plastic hinge. Then we have to apply the kinematic method to find the collapse load. So here let us now go to that problem. Simply supported beam with a load acting WU acting at a distance of 2 meters from here. So the mechanism will be like this. This is the mechanism for this simply supported beam. So since simply supported beam, you have R is equal to 0, number of plastic hinge to be formed to have mechanism is only one hinge. So now there is no hinge here, there is no hinge here because moment is 0 at the end. Hinge can form only at the point of maximum bending moment or under the concentrated load. Here point of maximum bending moment is also C. Concentrated load also acts at C. Therefore, there is a possibility of having plastic hinge at C. So this is the mechanism we can write. So here I have written at A there is no plastic hinge, at B there is no plastic hinge. Plastic hinge is denoted by a dot like this. Only at C it forms, and the mechanism will be like this. Now since the load is not acting at the center, you have different angles here. So this is theta, I will take this as theta 1. That means if you take the deviation here at C, this is the point C, you have this total deviation as theta plus theta 1. Theta plus theta 1 is the total deviation here. So now as per the kinematic method, so we have to equate the internal work done to the external work done to get the value of collapse load. Now let me take MP as the fully plastic moment of this section. Fully plastic moment of the section of the beam. So I am taking uniform MP here from A to B. So it is having same cross section as well as the moment, the fully plastic moment casting surface section is MP. So the MP value will form first at C because at C you have the maximum bending moment. The point at point C you have the MP value first. Now I am going to use the concept of internal work done equal to external work done. So this is the internal work done is equal to external work done. So this is the concept we have to use the kinematic method. So internal work done, what you have to take here is, it is the work done by the plastic hinges. So this is due to internal work done is due to plastic hinges, whereas external work done is due to external load that is going to apply. We are going to apply on the beam. So now the internal work done in this case, it will be, what you have to do here is whatever MP is there. So MP is there here. At A you don't have any MP. At B you don't have any MP because there is no plastic hinge forming at A and B. At C you have MP into that deviation theta plus theta 1. So that is the internal work done. This should be equal to external work done is nothing but the load acting at that C, at the point C, multiplied by the deflection. So WU is the load multiplied by delta. So this is the equation we are going to use now. So here MP you will be knowing, so you have to find out WU. So WU is the collapse load. So what is the value of WU? So for that, what we have to do is we have to substitute for this delta. Now one important thing you can observe, in this triangle, theta will be very small. So theta can be equated to tan theta. When theta is very small, theta can be equal to tan theta. Tan theta in this diagram, which is finally this delta by, this is 2 meters, so delta by 2. So therefore I can write delta is equal to 2 theta. This is one relationship. Similarly, this triangle if you take, theta 1 is very small, therefore theta 1 can be equated to tan theta 1. In this triangle, tan theta 1 is delta by 3. This will be 3 meters, this will be 2 meters. In other words, delta will be equal to 3 times theta 1. Now, if you observe these two, delta is 2 theta here, delta is equal to 3 theta 1 here. So what I can write here is 2 theta is equal to 3 theta 1, or theta 1 is equal to 2 theta by 3. So we have to get a relationship between this theta and theta 1. That relation we have to use here. We have to use here. Now what I will write here is, this is mp into theta plus theta 1 is 2 by 3 theta is equal to wu into delta I can write as 2 theta. So 2 unknowns will be converted to 1 unknown, so theta. Now if you simplify this, so this becomes mp into theta into 1 plus 2 by 3 is 5 by 3 is equal to, this will be wu into 2 theta. So here you can cancel this theta. So whatever is left, you can write like this: wu is equal to 5 mp divided by 6. 3 into 2 is 6. So this is the collapse load that can be applied. That can be applied on this beam. That means when the load reaches this value, knowing the mp value, you can find out wu. So once the load reaches the w value, then there will be a mechanism here. Beam mechanism will occur. So this is how we can solve a problem of finding collapse load in case of a simply supported beam. Similar exercises we can do for fixed beam, cantilever beam, and all those things. But here and also where the cross section of the beam changes. So any type of beam, we can find the collapse load using this equation: internal work done is equal to external work done.